if you're coming in late, I just reviewed yesterday's or Tuesday's class and put up a new reaction. I wasn't recording that, so doesn't matter where the camera's aimed, I guess. So you asked me to move the camera up. I graciously did that. And then I just didn't record it. That's the, you can't have everything. You can have the camera close and on, or close and off. Okay, so again, if we add X2 across an alkene, the two X's, Br here, this also works with Cl2. Chlorine is a really nasty compound to work with. You've probably seen bromine. You've definitely seen iodine. Anyone who's had any kind of surgical procedures probably had iodine slapped across them. It's a really good sterilant. Br2 as well is a good sterilant. It's a little too good. Here's kind of a rule of thumb. If it can kill bacteria, it can kill you. Right? This is why medicine is hard. It's actually not hard at all. We could have cured the coronavirus like day one. Just bleach anything that's got coronavirus on it. People too. Coronavirus is dead. Right? Injecting bleach is actually not wrong. That would kill the coronavirus, totally. Would also kill you. Right? So the trick to medicine is killing the bad thing and not killing the good thing. So iodine is a weaker sterilant than bromine. Chlorine is a gas. I don't think I've had a chance yet to tell this class. Gases are way more dangerous than liquids, and liquids are more dangerous than solids. All right? So anything that's going to hurt you or help you has to get into your system somehow. So an awful lot of medicinal chemistry isn't figuring out a compound that will kill whatever it is you want to kill or bind to whatever it is you want to bind to, but figuring out how to get that into the cell where it needs to do it, right? Like I personally have made probably 20 compounds that in a test tube kill tuberculosis really well. All right? For a while as a postdoc, I thought I was going to be famous. If you try to kill TB in a test tube, right, you don't have to get through all of this. And the compounds I made didn't do that. So they have to get somewhere. As it turns out then, I2 is relatively weak. So it can sterilize your skin. It doesn't really hurt your skin. I guarantee you, if you like bathe in I2 every day, you'll eventually hurt your skin. Br2, on the other hand, very powerful. Will burn you, it will just straight up blister your skin. Chlorine, you can walk into a cloud of chlorine and not even know you did it, and you breathe it, and you're toast. All right, so solids are pretty safe. I've held potassium cyanide, which is a poison. I've held it in my ungloved hand. The solid won't go through your skin. It's not volatile. I'm not saying that was a smart thing to do, but it wasn't terribly dangerous. If, on the other hand, HCN, so if you add acid to KCN, you get HCN, which is a gas, and now it's kind of everywhere and you breathe it in. Stuff you breathe in is really nasty. So lab safety, if you're dealing with volatile liquids that produce vapor, or if you're dealing with vapor, watch out. All right, so chlorine, I'm gonna put here that chlorine does this reaction. People don't do this except on an industrial scale. You don't want to go upstairs to our labs and use chlorine gas. It's toxic, it's hard to handle. Bromine is a liquid, it's easier to weigh out. Gloves will protect you. So I'm going to show a lot of chemistry with bromine. Most of the time, chlorine, Cl2 will work. Some of the time, I2 will work. Okay. So in this reaction, I've got bromine here, Br2, and this is actually an electrophilic addition. So the pi bond of the alkene is still being a nucleophile, a Lewis base. The Br2 is being an electrophile, an electron acceptor. Hopefully everybody's maybe thinking this, some of you are really thinking this, that this is a nonpolar molecule. This is not, like HBr, right? The H is partial positive, the Br is partial negative. HBr is a strong acid. BR is a nonpolar bond, right? But it's got this instantaneous dipole. So again, the electrons are flowing around these orbitals, and it's very polarizable. Bromine's a heavy element. The valence shell is, what is it, 4 or 5? 4. So it's a ways from the nucleus. When it encounters something that's electron rich, that sort of pushes the electrons the other direction. And in the instant, you get an instantaneous dipole. And then the pi bond will attack the bromine, and the bromine-bromine bond breaks. Again, those two arrows don't get us to the product. The product is going to put one Br on each of the two. It's going to break the pi bond, put one Br on each carbon. Right? If we break the pi bond, each carbon is going to need a new bond. And look at this. It's always going to be an anti-addition. The two BRs are going to add anti to one another. So we have to be able to explain that with our mechanism. So now here's the cool thing. You remember how, right up here, pi bond attacks the H. The H can't be bonded to two things. So the H has to go to one carbon or the other. Bromine, having, larger valence shell, you've got d orbitals involved, you've got an f orbital involved maybe, can bond to two things. And so this is going to go, this is a terrible mechanism I'm drawing. In the instant, this is what we'll have. Right, we wind up again with a 3-center, 2-electron bond. The two carbons both bond to that bromine. Those are really weak bonds. And you can think about this as either structure. This could be both of those. They're essentially resonant structures of each other, even though you're breaking a connectivity. So they're not formal resonant structures of each other, but this is basically what you have. And you just have a lone pair, right? We have lone pairs on that bromine that can clamp back down there. And so really, the most stable structures having both carbons have a full octet. They both have a bond to bromine. All of a sudden going right to left. And here's another thing. This came up in the office hour last night, so I want to make sure to get it recorded and set in front of you guys. There's a word I left out. I'm sure you remember we had a snow day a few weeks ago, right before exam 1. And we sort of lost %EE, some stereochemistry stuff. And I said I'd come back to that. And I said, I am going to come back to that, but I didn't think there was anything all that urgent. There's a word that's really important. All right? So in this attack, right, you've got the pi bond attacking the Br2. Both of those compounds are achiral. And so as you think about it, if the eraser is Br2 and my hand is the alkene, right, it can set down on top, it could come in from the bottom. Remember, the pi bond's got electron density above and below the carbon-carbon bond. There's no preference there. Sit down on top of the Br, come up from bottom of the Br, front, back, right, left. There's no difference there. Okay, so that means you're going to get a 50-50 mix. When these two interact, I've drawn it with the BRs up. This is actually a mesostructure, so it doesn't really matter. But even if it wasn't meso, you'd get 50-50. I wrote enantiomer, it's meso. You know what I mean? Here's what we call that. All right, I'm going to put this word up over here. This is a word you need to know. You may have seen it in Wiley Plus. All right, a racemic mixture, or we would sometimes call this a racemate, is a 50-50 mix of enantiomers. I see folks writing that down. That's just a definition you need to have in your head. Now, anytime two achiral molecules produce a chiral molecule, and again, I see that that's not what's happened here, but anytime that happens, two achiral molecules produce a chiral molecule, that chiral molecule has to be a racemic mixture. The only way to get a non-racemic mixture, or one enantiomer in preference of the other, something chiral has to be involved. It could be a reagent, a catalyst, but something in there has to be one enantiomer only. It has to be optically active. That's another word we'll get to. All right. So as you look at these addition reactions, anytime anything adds to a carbocation, carbocations are planar. Attack can come from above or below, right, left, front, back. Same thing with an alkene. This alkene is planar. It can sit down on the bromine. It can come from the back, come from the right or the left. All right, so you're going to get a 50-50 mix. Now, I know the board, I know I've totally lost control of like the first full board I've used in the class today. What I would like you to do now, I'll give you a couple of minutes for this. Go from, let's call this structure 1, and I'll call this structure 2. Go from 1 to 2. Draw me the curved arrows you would need to account for what's happened there. This is there's only one more step in this reaction. We go from, and 1 includes everything over here. Go from what's circled there to the product with curved arrows. Okay, so if you see a problem like this, and this is like a real chemical problem. This happens to us sometimes up in the lab. Like we'll go in the lab, we'll do a reaction, we won't get the product we expected to get. Happens all the time. To solve that, we have to figure out how the product we got happened. Because maybe there's a way, if we can figure out how it happened, maybe we can stop it from happening and make what we want to have happen. So what you want to look at is, the questions you want to ask is what bonds form and what bonds break. All right, I'm actually going to redraw this. Because I think that board was getting cluttered. So this is the reaction we've got. This is the starting material, the intermediate, and the product. So I gave you the arrows on the first one. The pi bond is going to attack the bromine. Bromine-bromine bond breaks so that the tail bromine, the rightmost bromine, gets the bonding pair it was sharing with the other bromine. right? Neutral thing gets electrons, it becomes negative. By the way, this, if you're reading the book, this is going to be called a bromonium ion. You'll also see chloronium ions and iodonium ions. All right, so now what I asked you is to go from here to here with curved arrows. So which bonds break? Which bonds form? Look in here, this bond breaks. Right? And if we look in the product, that bond forms. And that's it. So now the curved arrow in a mechanism, the curved arrows have to account for every bond that breaks. They have to account for every bond that forms. And they have to do nothing else. Right? So you can't have a curved arrow, like nothing happens to this carbon. It's a CH2 on the left, it's a CH2 on the right. Don't draw any curved arrows to or from it. All right? It's just going to sit there, nothing's going to happen to it. No electrons are going anywhere, it's just floating around. So the curved arrows then, to break this one, right, and this kind of makes logical sense. The arrow is going to start with the electrons in the bond and go to that Br there. All right, that neutralizes the charge. This Br stays up. The second bromine, we need to make a bond to this carbon. And so the arrow goes from the negative charge or a lone pair on that bromine to the carbon. Okay, so if we have an arrow from electrons on an atom to an atom, so from one atom to another, that's going to make a bond. You're not moving a lone pair from bromine to the carbon. You're making a bond. And so the way this works is the bromide is a nucleophile or a Lewis base. This carbon has a partial positive charge. Remember, we've got this kind of structure here, right? There's significant partial positive charge on both of these carbons. So the nucleophile, the thing with the Lewis base, is going to hit this partial positive carbon. That carbon can't have 5 bonds, so that's going to break this bond and kick electrons onto the bromine. The electrons are going to funnel from the thing with electrons, the electron donor, the base, to the thing that lacks electrons. Okay? Yep. Yeah, so what happens here, this is a weird one. I try to fly past that. Somebody asked that question. Right? The two carbons share the pair of electrons. So when these two pi electrons make the bond to bromine, the electrons are shared between the two carbons, so they can, because bromine can have more, bromine can expand the octet. It can have a lot of bonds. And it can change the number of bonds it has in a way that second row elements don't do. And so it really works out that you get the real structure for this bromonium ion is sort of all 3 of those, right? It doesn't follow the rules we teach you about resonance structures where you can't change connectivity because you are breaking a sigma bond. But it behaves like resonance in that all 3 of those sort of exist at the same time. And so what happens is the 2 carbons and the 1 bromine end up sharing 2 electrons. So we call this a 3-center 2-electron bond. Like most of the bonds you guys see are 2-center 2-electron bonds. 2 atoms sharing 2 electrons. If 3 atoms share 2 electrons, the bond is going to be really weak, right? So that carbon-bromine, it's the problem of drawing Lewis structure. By drawing these as full bonds, they look like they're regular bonds. They're really like half bonds each. I don't know if that's a sufficient answer. It's not a great answer unless you do some quantum mechanics. Yeah.
So why is it like the reaction?
We'll get to that in a second. Yeah. So The thing about the stereochemistry, this mechanism, right? This mechanism explains the stereochemistry. If we use one of these cations, right? This positive charge is trigonal planar, it's flat. Nucleophile can come from the top, come from the bottom. But clearly, based on the product we get, the nucleophile doesn't come from the top or bottom, it comes from the opposite. And really what's happening here is this bromine, the bromine in the bromonium ion is sort of sitting on top. As I've drawn it, it's sitting in front of the board, protecting attack from in front of the board. So the nucleophile has to come from behind. And that's all we see. So the two things add anti. If it's a ring, you'll get a trans disubstitution. If it's not a ring, it's kind of hard to see that it was anti, but it is always an anti-addition. Okay. So which side is favored? What you have to add up here then is the bonds that break and the bonds that form, right? So overall, we're going to break a bromine-bromine sigma, we break a carbon-carbon pi, and we form two carbon-bromine sigma bonds. So I don't have the number, you don't have to know the bond energies. You do have to know, that this reaction favors the right. But if you go in and add this up, two carbon-bromine sigma bonds are stronger than a bromine-bromine sigma and a carbon-carbon pi. Remember, the pi bond is a carbon-carbon pi bond, any pi bond is significantly weaker than a sigma bond. Because the overlap between the p's are not as good as the overlap between the s's. Okay. And also, the bromine-bromine sigma is pretty weak. So this works out. The right side is favored for Br2 and Cl2. I haven't talked about this either. I think I did way back when. Bond strength depends on how well the orbitals overlap. Right? So a carbon is a second row element, can't expand the octet. Carbon, nitrogen, oxygen are all sort of the same size. So a carbon-oxygen bond, a carbon-carbon bond are pretty strong. Those orbitals overlap, they fit together nicely. As you go down the periodic table, the atoms get bigger. So down at iodine, iodine's this giant orbital, or atom. And so you have this carbon sp3 orbital trying to overlap with an iodine sp3 orbital that's huge. The iodine can't get as close. The orbitals don't fit together well. Again, I like physical analogies. I keep saying this, and I'm not trying to turn anybody off or dismiss you. To really understand all the electronic behavior here, you need to do mathematics and use quantum mechanics. The physical analogy is shaking hands. I once had the opportunity to meet a basketball player we were recruiting who was interested in engineering. He was 7'6". All right, I'm a big guy. All right, there's nothing to brag about. I was born big, and I'm a little overweight. But I'm used to being bigger than people. It's a little weird to me when I'm not bigger than people. And this guy was like I felt like a little kid. And I shook his hand, and it's like he just grabbed my arm. Right? Like we couldn't shake hands that well. On the other side, have you ever tried to shake a baby's hand? This is not something people do. You don't start, and we don't shake hands anymore at all. This is going to be a dying analogy. Try to shake a baby's hand sometime. Just go out in public, find a baby, try to shake its hand. See, hilarity will ensue. But if you do, your hand, you can't shake its hand. Its hand is tiny. Handshakes between normal-sized adults, the hands are roughly the same size. Some people have big hands, some people have little hands, but they're more or less the same. 7'6" guy that can completely encompass the basketball, that's a crazy sized hand. baby who like won't even open their fist. Like that's bad. So the average adult with a baby is like a carbon iodide bond, right? They just don't overlap that well. 2 average-sized adults, that's like a carbon-carbon bond, so the bond's stronger. So basically, bonds far away up and down the periodic table are weaker. So for this reaction, if we make 2 carbon-chlorine sigma bonds, we get 2 pretty strong bonds. All right, and this reaction really favors, we make 2 sigma bonds, we break a sigma and a pi. So we really turn a pi bond into a sigma bond. And that is downhill in energy. It's definitely downhill in enthalpy. It's still downhill for bromine. If we turn a carbon-carbon pi into a carbon-bromine sigma, that is downhill. Not by a lot, but enough. For iodine, this is not. The equilibrium constant here is about 1. So if we do this reaction with iodine, like the what that says is basically the carbon-iodine sigma bond is roughly as strong as a carbon-carbon pi bond. So it's not that the reaction doesn't happen, it just doesn't go to completion. That's going to be important for the next reaction I'm going to show. I'm just going to show it. Stay. All right. So this is the Halohydrin reaction. The book is probably going to tell you ROH is water, but ROH can be any alcohol. It can be water, so R could be H. R could also be methyl or ethyl or propyl or something like that. This reaction works with all the halogens except fluorine, right? In the end, we make 1 CX bond, so C halogen bond, but we make 1 CO bond. The CO bond is really strong. And so this lets us, because down here the equilibrium constant's about 1 for iodine, so we do get this iodonium ion. I'm going to go through the mechanism here in just a second. So you get this ion, and then instead of Br minus or I minus attacking, you get an alcohol attack, or an O attack. All right, so let's do the mechanism. First step of this mechanism is the same. And again, now this is a chiral ion. The bromine can attack from the top or the bottom. The alkene can sit on the bromine from the top or the bottom, the right or the left. You don't have to draw both of them. And actually, I won't even get carried away. You need to be able to answer the question if I ask you what the stereochemistry is, all right? The alkene's achiral, Br2, I2, Cl2 are achiral. So this product has to be achiral. Same thing over here. This final product, this is a chiral molecule. This has to be racemic. So we get the enantiomer as well. Yep. Here. Chiral center, no plane of symmetry. Yep. Okay, so now here we are. We get that bromonium ion. We typically, if you want to do this reaction, you're typically going to use the alcohol or water as a solvent. And you have Br minus. So we have a lot of this one, and we have one Br minus. And the other thing you have to keep in mind, which one of those do you think is a better base? Which one of those is a stronger base? Let's say it's water. Water or Br minus? Which one is a stronger base? Everybody's saying yeah, so the minus. Everybody wants the minus to be stronger. So let's do this. Which side of that equation is favored? You think we got to vote for the left? I'm probably not having a poker face on that one. I suppose poker rooms are still open with masks. I know you're really worried about this, but it just occurred to me, like, a mask would really help in poker. Like, anyway, I'm just wondering what would happen if I went to Vegas and walked in and insisted on wearing a mask to the high rollers room. Probably nothing good. All right, so is HBr a strong acid? It is. H3O plus is also a strong acid. HBr is one of them that you might, if I'd said HCl, would you have also said the left? So HCl, HBr, and HI are all strong acids. And you might have learned that strong acids completely dissociate, as if the acid is what's deciding that. Again, the base has to do this. So water is going to take a proton from HBr. You're going to get H3O plus and Br. And this reaction actually favors the right by a lot. Okay? pKa of HBr is like -6 or so. H3O plus is about 0. And again, you wind up with the charges. And I've had this discussion several times, and it's one that takes a little while to adjust to. Charges don't make molecules stable. So your gut feeling that a charge is destabilizing is a good one. The trouble is it's not the only thing that matters. There's a lot of factors that go into stability, and charge isn't the only one. So sometimes the other things are more important. Okay, so any strong acid. Strong acids are really defined by, if you put them in water, the reaction to the right, with water being a base, is completely, it goes to completion. Yeah. No, I think, yeah, the middle one's all right. Okay. So what this means, if you look at this equation, right, this is going to be the weaker acid, and this is going to be the weaker base. The fact that this reaction favors the right means that water is a stronger base than Br minus. And so here, down here, for those of you at home, I'll read this in just a second. It might be hard to see. All right. So what you really have, you wind up with this bromonium ion, and now you have a lot of a stronger base and one weaker base. Right? So what's going to be the base in this question? If we just had one of each of these, the stronger base would be the one you'd expect to be the base, right? The stronger base and the stronger acid always react before the weaker ones. If they were equally strong, right? If water and Br minus were equally strong bases, the one that you had more of, you would expect to react. So in this case, the one that you have a lot of, the stronger base, is going to react. You have a lot of strong base, so it's going to react. it attacks that carbon from behind. Remember, the bromine's sitting, the way I've drawn this, it's sitting in front of the board, so the O has to come from behind the board. You also have the enantiomer where the bromine's behind the board. Now the O would have to come from in front. So you get anti-addition. Oop, crap. Hang on. Sorry. I'm screwing up. All right. So the oxygen is going to attack the carbon I've just shown. I'll explain that in a second. And then it's going to break this one. So you're going to get the O and the Br to be anti to one another. I'm sort of showing, I'm drawing the enantiomer of this thing. So, hang on. All right. So that's the next step. We've got a C of ROH and we still got Br minus. So before I talk about how, I'm going to talk about the reaction a little bit more. Draw me the arrows you need to do, the curved arrows you need to go from what I've drawn down here to the enantiomer. Again, remember, we've got enantiomers here, so we've got a bunch of stereochemistry issues. Okay, so we've got an 8. The only difference between these two is this proton. So this last step is just a Bronsted acid-base proton transfer reaction. And honestly, at this point, I don't really care which base you use to pull that proton off. But again, the one you're going to use, the one that will really happen, we've got a whole bunch of a stronger base and we've got one of the weaker base. So at this point, ROH takes the H. We neutralize that charge, and this gives us the enantiomer. The whole way through, though, we've had the enantiomer. So when you do this, if you, like, let's say I put this exact question on the exam next week. You weren't the only one. There were many dirty looks there. All right, so if I do that, you can show any of this. You could, they have to, the important thing to have here is the OR and the BR have, or the X, could be I or Cl, have to be trans. They have to be anti to one another. The other important point here, and I kind of glossed over it, you saw me sort of erase this. The nucleophile here is going to attack the carbon that would be the better carbocation. And when I say better, I mean more stable. Okay, so at this point, the ROH can either attack the secondary carbon or the tertiary carbon. Right? It's going to attack the tertiary because that would be a better carbocation. Basically what that's saying is there's a partial positive charge on both carbons. That charge is, more of that positive charge is going to be on the tertiary carbon because it's more stable. And then the attack, ROH is going to attack that carbon from opposite the Br. Right? So the O and the Br are going to end up trans to one another. I'll do another example of this. All right, draw me a product there. All right. So again, Halohydrin conditions, ROH. In this case, the ROH is water. So R is H. And if you look at this, you're going to add OR to the carbon. So with I2 in water, we're going to add I plus an OH. All right. These will be, they will add anti and OH So we're going to add I and OH. The I and the OH will add anti to one another. The OH is going to add to the carbon that would be, like if you just look at the two carbons and you say which one of these carbons would be the more stable carbocation, that's the one that gets the OR. So again, tertiary versus secondary. So the I is going there, the OH is going there. I've given you a gift. Right? The carbon that the OH adds to has two methyls on it, so even at the end of the reaction, it's not going to be a chiral center. So it's going to be actually impossible to tell in this product if the addition was anti or trans. Probably a lot of students are going to want to come in here and, all right, so they would give me I, and then you'd have to have that be a methyl, and that would be an OH. And that's fine if you want to do that. Like if you just want to emphasize to me that you know these are anti, that's fine. But you wouldn't have to do that. Because this is not a chiral center, just drawing it as a, you know. And actually because it's going to be racemic, the addition is going to be both 50%, you know, it's going to be 50-50 mix of enantiomers. You don't have to show any stereochemistry on this one. What was your question? Sorry. Okay. If you do go in here and draw lots of wedges and dashes, you probably should write plus enantiomer or racemic there, just so I know you know that you're not making an optically, you're not making an enantiopure molecule. Yep. So it's this carbon, if we go back up to the mechanism, again, the nucleophile, the base, the alcohol, or the water, is attacking a carbon based on its partial positive charge. So the carbon that would be the most stable, it's almost reversed. Like if you hear it's the more stable cation, Well, then shouldn't the other, if it's like the more stable cation should be more stable and wouldn't react as fast as the other. But what that means is that carbon is bearing most of the positive charge of the two carbons.
The OR, in this case it's OH, is going to always take the more stable.
Yeah. And the other thing that's important to point out here is you don't have any base in this that can take off this proton, all right? We don't have hydroxide attacking that carbon. We have water. So down here, all right, so we have the iodonium. The thing that attacks is neutral water. And then you lose the proton. All right, so you don't have any way to make hydroxide. And you're going to be tempted, and most of you will do this at some point. Hopefully you do it in a practice. You're going to use hydroxide. Because, like, it's logical. If you get to here and you're like, I just need an OH there, I know hydroxide, just bang, I'm done. Be done with this and go do something else. All right? But you don't have any way to make hydroxide. Right? There's no base in this. I didn't give you hydroxide. I didn't give you any bases that could pull a proton off of water to make hydroxide. Okay. Any of you see the helicopters this morning? Yes. Is it cool? I meant to get over there. I saw that email. I'm like, I got to get over there. But I had a meeting at 11. Well, I had a meeting I could have been a little late to. And I just didn't get over there. Anyway, do we know when they're coming home? Okay, good. I can just go sit over on Poteet. Now I need to move the camera. And I should probably turn the camera off at this point too, right? Like that. See how that... Oh no. How about I carry the little mobile computer with me? Oh no, that works. No, that's not going to work. Sure, that'll work. Okay. So as a little interlude, I'll let you guys write that down. So this reaction is a hydrogenation reaction. You guys have seen this terminology if you've read ingredient lists. A lot of fatty acids are, you've all almost certainly heard the term unsaturated fat, unsaturated fats, saturated fats. That refers to the saturation like a double bond, like units of unsaturation. So a lot of fatty acids in nature that we eat and that compose, some or more of our bodies are saturated. So they have, basically a fatty acid is going to have a carboxylic acid head long hydrophobic tail. That hydrophobic tail often has a double bond in it, or multiple double bonds. And so partially hydrogenated vegetable oil, you might have seen that. It turns out that the double bonds affect the melting point and the physical properties and the chemical behavior of the fats. And what people found quite a while ago is you can make them easier to deal with if you hydrogenate some of those double bonds. So this is a hydrogenation reaction. We take an alkene, hydrogen gas. I've drawn palladium here. Palladium's probably the most common. I say any transition metal. It's not any transition metal, but I'm fine with that for this class. Palladium's the most common. Platinum does this. Nickel does this. Rhodium does this. Iridium does this. Copper, silver, and gold really don't. The others do a little bit. Ruthenium some, rhenium some. Anyway, palladium's the one you want. Palladium's also really expensive. And when I say no mechanism there, I will not ask you to draw the mechanism of this reaction. The mechanism's pretty funky. Basically, hydrogen reduces the metal. So then you get these two H's sticking up from the metal surface. I'm not on camera, probably. Right? So the hydrogen comes in, sits on the metal, reduces the metal. You end up with a couple of hydrogens sitting there off the metal. Then the alkene comes and sits on these, takes them away. So the two H's that go on cis. We call this a syn addition, S-Y-N. All right, so it's a reaction you'll see. I might ask you to draw a product or give you the starting material and the product, and you tell me the reagent. We'll probably use it more when we get to the synthesis bit. So it's a reaction you need to know, but you're not going to have to draw a mechanism for it. All right, epoxidation. All right, so this reaction ought to look superficially kind of familiar, right? The product on the right is called an epoxide and it's a fairly common industrial functional group. It's used in, well, it's used in a lot of things. It looks like the bromonium ion, right? So it looks like this halonium ion where the pi bond attacks, right? The pi bond attacks the bromine, and both carbons end up bonded to a bromine. So here the pi bond attacks, believe it or not, this terminal oxygen of a per acid. I've written this kind of small. The per acid I'll draw the whole thing. So this would be called a per acid. So it's a carboxylic acid, but instead of an OH, it's got an OO bond there. So the OO bond is a peroxide bond. You guys know hydrogen peroxide, right? H2O2. Pour it on your scabs, bubbles up. So this reaction's general for per acids. I have no idea. I mean to look this up like every semester I get to this part. I'm like, I should look up why metachloroperoxybenzoic acid, MCPBA, is so much. I mean, I've got like a kilo of this stuff upstairs in my refrigerator. The one in the lab, not my office. It's cheap, it's abundant, it's the one everybody uses for this. I don't know why. Really, any per acid will do it. So, right, that functional group is the bit that's doing the epoxidation. So you don't need to know the mechanism for this reaction either. that might sound friendly. Sooner or later, you're going to think reactions that you don't have to know mechanisms for are BS. But right now, that's 2. Here's a reaction that you do. And you kind of already have seen it. So that 3-membered ring epoxide, there's a lot of ring strain. I don't know if you remember that phrase from back in like chapter 1 or 2. But the bond angle of a 3-membered ring is 60-ish. Right? The geometry means that like the 3 angles inside there can't be 109.5. That would not be a triangle. So there's all this ring strain. The geometry of the atoms prevent the orbitals from overlapping to make strong bonds. So the carbon-oxygen bonds are fairly weak. And so if we treat an epoxide with an acid, and this is going to always have to be a strong acid. Usually it would be sulfuric acid, it could be HCl, it could be a sulfonic acid of some sort. But any strong acid and a nucleophile. Again, ROH is going to be an alcohol or water. The reaction that happens is this one. Okay? So what has to happen here first, the epoxide is going to be protonated by the acid. And now that thing looks a lot like this halonium ion, right? You got a 3-membered ring, you got this positively charged atom bonded to 2 carbons. Those 2 carbons now are really electrophilic. They're good Lewis bases. And so the nucleophile, again, neutral nucleophile here, can attack from opposite the OH, the protonated O. You break open that 3-membered ring, and what drives this reaction is relieving that ring strain. So we go from 2 really weak CO bonds to 2 pretty strong CO bonds. All right, and then A minus or ROH, water, some base has to come in and take that proton off. So this is a way of getting 2 oxygens. We can take an alkene, and we can, in 2 steps, put 2 oxygens on the 2 carbons, and we can put them on trans. Okay? So really the mechanism for this is just the same mechanism you have for the halonium ion. As you go through and you start trying to deal with mechanisms, try to group them into types. You're always going to have something with electrons attacking something that doesn't have electrons. But they'll sort of be mechanistic types throughout the reaction. And this one goes the same. So this is an anti-ring opening. The ROH is going to attack the more substituted carbon. In this case, right, the 2 carbons are identical, so it doesn't matter. But just like the Halohydrin reaction, the nucleophile is going to attack the more substituted carbon. And then you're also going to get, we go from achiral stuff, we get a chiral molecule, so we're going to get the enantiomer plus the enantiomer here. It's going to be a racemic mixture.
Can you just explain what's going on in that bottom right corner one more time? Sorry.
Yeah, so, all right, so we protonate, the first step is to protonate the oxygen in the epoxide, right? So now that makes the ring electrophilic, electron poor, makes it Lewis acidic. The neutral, so alcohol or water, whatever it is we have there, has electrons. Okay, so it's going to attack, and it's going to do that, like if it's water, it's going to attack as water, not hydroxide. Right? We're under acidic conditions. It's a little easier to see this than in the halonium. If I've added sulfuric acid to this to catalyze it, I don't have any hydroxide to add here. So water or methanol or ethanol, whatever, attacks, that H comes along for the ride. If you look at this mechanism, I haven't done anything to the OH bond. No arrow to from that OH bond. So that OH is still there. Obviously, I have to get rid of it in the end. Now that hydrogen, in the alcohol, this hydrogen is not very acidic. pKa of that hydrogen is about 17. Over here, that hydrogen's on a positive O. pKa is now like 1, 0, -1, something like that. So now either A minus, the conjugate base of the acid, or it could be another molecule of ROH. I don't really care what you use there. Takes that H to give us the neutral product. All right? All right, so far you've learned Markovinikov additions. Right? If I add HBr to an alkene, the H goes on the less substituted carbon, the Br on the more substituted carbon, because we go through the more stable carbocation. The concept of doing the reverse of that, so doing an anti-Markovinikov addition, is a concept you guys should keep in mind as you develop your careers. Right? So a lot of money gets made, a lot of prestige gets made by taking something that's fairly common that people do and, subverting it somehow. So like I said, Markovinikov, I mean, seriously, he was working in like the 1870s. Like the fact that these guys could figure out or could do any chemical research when they had no real way of, they didn't even know what an atom was or how to identify things. They were incredibly skilled, like practical material manipulators. Anyway, Markovinikov figures out how to add HX to alkenes, where the H goes, where the X goes. As a synthetic tool, you're limited by that, right? I can't, if I've got an alkene and I want to add a Br, I can only add it to this one carbon. So if the person who figured out how to add the Br to the other carbon, I guess he didn't get that famous because I don't know who it was. But at the time, like that's a big paper, that's an industrially useful process. And so it turns out that what you have to do, same reaction basically, but you put in peroxides. H2O2, benzoyl peroxide that you guys are using in the lab this week. Something that will initiate a radical mechanism. So that to do an anti-Markovinikov addition, you can't have a carbocation. Right? If the carbocation's involved, you're going to get Markovinikov addition. So the mechanism has to be something that isn't a carbocation. Turns out the way to do it is to have a radical mechanism. I'm not going to ask you guys any radical mechanisms. I mostly am doing this for illustrative purposes, to think about other ways of doing things. You can also do an anti-Markovinikov addition of water. Again, I'm not going to ask you the mechanism for this. And again, it uses peroxides. Right? So if I treat an alkene with borane, BH3, or really any molecule that's got a single BH bond, the H and the B add across that double bond in exactly the way you'd expect, right? Well, based on their polarity. So the HBr polarity, sorry, the HB polarity is the reverse of an HBr polarity. And then you can cleave the carbon-boron bond to make it a carbon-oxygen bond with alkaline peroxide. A guy named Brown did this, won a Nobel Prize. All right? The anti-Markovinikov addition of HBr with peroxides didn't win a Nobel Prize because it happened before they gave Nobel Prizes. But doing an figuring out how to do an anti-Markovinikov addition of water, HOH, that happened in the 1940s and 50s. Guy wins a Nobel Prize, gets very famous, lots of chaired professorships. All right, so I'd like you to be able to recognize those reactions, predict the product for those reactions. Just know that if there's boron, or so yeah, BH3 and then peroxide, that's going to be an anti-Markovinikov addition of water. HBr and peroxides, it will be an anti-Markovinikov addition of HBr. I think I'm off screen. So right there is where we're going to draw the line for exam 2, which is a week from today. A week from today, right now, you'll be done. It's just a week. So anyway, I'm going to get out to you this afternoon a topic list of what you'll have to be able to do on exam 2 that hopefully will guide your studying. So I've got another office hour tomorrow morning. I'm sorry about this morning. I thought it was 9:30. Turned out it was 9. I got there by 9:30, kind of. I will have an office hour tomorrow, and then I'll have ample office hours next week up until, so Monday through Wednesday, and then I won't be available the rest of the week as I dive into grading. So enjoy the rest of your day. Yeah, that's it. See ya.